So, welcome to today's lesson on the householders method, and we'll be taking an example of a 4x4 matrix. So, in this video, we are going to take our time to make things very simple for all of you. So, I'm Bodo Kranrindo, a third year student of mathematics KNUST. So, we have already discussed the householders method and the algorithm, and we solve an example using a 3x3 matrix. So today we want to upgrade to a 4x4 matrix. So before that, let's remind ourselves of certain things we learned. So we said that the householders method is used to change a symmetric square matrix into a tridiagonal matrix with the same set of eigenvalues. So that means that your original matrix A, if you convert it to that tridiagonal T, they should have the same set of eigenvalues. So to do this, we use a householders algorithm, and we always do n-2 iterations, where n here is the dimension of our matrix A. So here, where n is the dimension of the symmetric matrix. Alright, so we like to go through the householders algorithm. So this is the algorithm. The algorithm says let n be the dimension of A. So for k equals 1 to 2 up to n-2. So we always do n-2 iterations. This is the formula for computing for your alpha, and this is the formula for computing for your r. Then we always say w1 of k up to wk of k is equal to 0. Right, so this is the algorithm. We've explained in our previous video. Don't worry, as we use it to solve the example, we will explain how to use it. And we have this also here. We have that also here. So this for finding for your wk's, your wj, and this is used to find for your h matrix, and this is the formula for finding for our a. Alright, so an example. So we have to use a householders algorithm to transform this symmetric matrix into a tridiagonal matrix. Alright, so before that, we have to verify if our a here is symmetric or not, because if it's not symmetric, we can't use a householder on it. So the question said it's symmetric, so that means you are good to go. So you should know that it's not any matrix that you can perform the householders method on it. You have to make sure that the matrix is symmetric. Alright, so that's A is equal to A transpose. Right, so the determinant of A is negative 37. Right, so the reason I'm finding the determinant of A is that after we've gotten our tridiagonal system at the latter end, we like to know whether what we did is correct or not. So if what we did is correct, then the eigenvalue of that tridiagonal system should also be negative 37. So have that in mind. So our matrix here is symmetric, so thankfully we are good to go. So from the algorithm, you realize that this is a 4x4 matrix, and as a result of that, our dimension n is equal to 4. So that means in this video or in this question, we are supposed to do n-2 iterations, and n is 4, so that means we are going to do 2 iterations. So with the first iteration, that means our k is equal to 1. So when our k is equal to 1, this is the value for our alpha. Alright, so let's get it from the algorithm. So realize that the algorithm is alpha is equal to negative sign of ak plus 1 ak and whatever we have here. So when k is equal to 1, then that means you're going to get alpha will be equal to minus the sign of, so k is 1, so 1 plus 1 2, so a2 1, then all times, so I starting from k plus 1 to n. So that means we're going to have a2 1 squared plus a3 1 squared plus A41 squared all raised to the power half, as you can see here. So that becomes the formula for computing our alpha. So you can see that here. So when k is equal to 1, that's for the first iteration. We have our alpha given by this, and our A21, A31, and the A41s are from the question. So the minus the sign of A21 here means that we look at A21 in our matrix. So this is our A21 and this is our A21 too, because the matrix is symmetric. So realize that the sign attached to it is positive. So that means you are going to have minus here times positive, which will still give you negative. So that's the reason we have this negative sign here. Then we come here, A21 squared plus A31 squared plus A41 squared. So we can also get that from our matrix. To realize that this is our A21, A31, A41. Or since the matrix is symmetric, this is the same as A21, A31, A41. Alright, so that's what you can see here. So 1 squared plus minus 2 squared plus 2 squared all raised to the power half. And when you do this computation, you're going to get negative 3. So that means that in the first iteration, our alpha is negative 3. Then to get our r is 1 over 2 alpha squared minus 1 over 2 alpha A21. So note that from the matrix, our A21 is 1. We've already found that. So inserting that into the formula for r, we are going to get r to be equal to root 6 when you make the computation. Then it comes to finding our w's. Remember that from the algorithm, we said that w here, w1 of k is equal to this is 0. So realize that here our k is what? 1. So that means that w1 of 1 will be equal to 0. So because you are doing the first iteration, our w1 will be 0. So you can find that here. So our w1 is 0. Then our w2 will be equal to A21 minus alpha over 2r. So from the algorithm, okay, so we are referring to the algorithm. So remember we said wk plus 1 is equal to what we have here. So remember, since you are doing the first iteration, our k is 1. So that means that w1 plus 1, which is w2, is equal to ak plus 1. So a21 minus alpha over 2r. So that's the reason why we have this formula here for computing our w2. So our w2 will be equal to our a21 is 1, then our alpha is negative 3, our r is root 6, so 2 times r is 2 root 6. So when you compute our w2, we get root 6 over 3, and you are supposed to compute our w3 too. So our w3 from the algorithm, our w3, so to compute our w3, realize that here we have for j equals k plus 2 up to n. So k is 1. So that means that for j equals 3 up to n. Here n is 4. So from 3 to 4, our wj will be equal to ajk over 2r. So that means that w3 will be equal to a31 over 2r, and w4 will be equal to a41 over 2r. So note that um our a3, this is our a31 and this is our a41. So we are going to bring that one here to realize that our a31 is given by this formula here. So when you insert in our values, you're going to get this to be w3, and this is our w4, a41 over 2r. So when you make the insertion to, we get root 6 over 6. So that means we have our values for alpha, r, and w's, right? So we can form our matrices. So we have our h here is equal to I minus 2 omega omega, or ww transpose. So to find ww transpose, we know ww transpose is given by this matrix here. So since our w1 is equal to 0. That means each component of our matrix here which contains W1 will be 0 because 0 multiplied by any number is 0. So that means since this component has 0, 0 throughout, our first row is going to be 0. And you realize that our first column too has W1 inside throughout. So that means that our first column is also going to be 0. And you are going to be left with this. I hope you get it. So that's what you can see here. You're going to be left with this. Alright, so remember we've already found what W2 is, W3 is, and W4 is. So we just multiply them. Alright, so when you multiply the values for W that you've already found up there, then you are going to get this particular matrix here to be WW transpose. I hope you get it. Alright, so after getting this matrix here, then remember that your H is given as I minus 2 omega omega transpose. So this is your I. Your I is the identity matrix. So since you are dealing with a 4x4 system, this is going to be our I. So minus 2, and this is the omega omega transpose we just found. Right? So when you do this computation, you're going to end up with this particular matrix here, and this is going to be our H of K. So it is H of K, and here K is 1. That's why you can see 1 here. Alright, so since we have our H, that means we can find our first transformation matrix. So our first transformation matrix. So our first transformation matrix, A1 or A of 1 is equal to H of 1, then A of 0, then H of 1. So the formula is given as A of K is equal to H of K, then A of K minus 1, then H of K. So that's the reason you can see this here because K is 1. So all this is from the algorithm. So you realize that we have that here, and what we just did for the H it can be found here. So the A not here also stands for the original A from the question. Okay, so when you do this, so your H, this is your H1, then your A is from the question. So when you do the matrix multiplication, you're going to get your first transformation matrix to be whatever we have here. This for negative 3, 0, 0, negative 3, 10 over 3, 1, 2 over 3, 0, 1, everything here. So note that we got this from the product of these three matrices here. So our H, which is this, H of 1, which is this, and our E not, which is from the question. So let me show you. So which is from the question, this one, right? When you do that, you end up with that particular matrix that we have found. Alright, so we are done with our first transformation iteration, and you can see that we still don't have a tridiagonal system because for a 4x4 system, our tridiagonal should be of this form: A11, A12, 0, 0, A21, A3, A22, A23, 0. You're supposed to have 0 here, A32, A3, 3, E34, so we'll have 0, 0 here, E43, and E44. So realize that we have 0, 0 here, another 0, 0 here. We are supposed to make this 0 and also make this 0. So that's the reason you have to go through a second iteration process, okay? So know that for the second iteration process, our key is equal to 2 because that's the second iteration. I hope you get it. So note that from the algorithm, the value for alpha is negative the sign of ak plus 1k, whatever we have here. So when k is equal to 2, that means you're going to get k plus 1 is 3, 2, and this is I is going to run from 3 to 4. So you're going to have a3 squared plus a42 squared all raised to the power half. And note that from our new matrix here, our A32 is 1. So our A32, so this is our A32 here, which is 1. You can see that's right. And our A42 is 4/3. So you realize that this 4/3 and negative 4/3. It's supposed to be negative 4/3. Alright, so let's do the computation here. So it's 4/3, so we don't have to have any negative here. Alright, so you realize that the sign of A32 is positive, so negative times positive gives us negative. That's why you can find this negative here. Then A32 is 1, A42 is 4/3. So when you make this computation, you're going to get alpha for the second iteration to be negative 5/3. Then our R is given as 1/2 alpha squared minus 1/2 alpha 8k plus 1k. So since our k is 2, that means the value for our R is going to be this. So we are going to have A32 here. And note that our A32 is just 1. So inserting the values, you are going to get whatever we have here, because alpha is negative 5/3 and our A32 is 1. So after making this computation, our R is going to be root of 20/9, which gives us 2 root 5/3. I hope you get it. Alright, then note that we've already set our W1 to be 0. So in this case, since you are doing the second iteration, our W2 will also be 0. Then for our WK plus 1, remember it was equal to AK plus 1K minus alpha over 2R. So here K is 2, so you are going to have K plus 1, which is 3. So W3 will be A32 minus alpha over 2R. So our A32 from our first transformation matrix is 1. This is our alpha for the second iteration process. And this is our R. So making this substitution is going to give us 2 root 5/5. That happens to be the value for our omega-3 or W3. Then remember that we said for J equals K plus 2 to N, our Wj is equal to AJK over 2R. So here our K is 2, so for J equals 2 to N, and N is also 4. So from 4 to 4, we have W4 will be equal to A42 over 2R. So that's the formula you can see here. So A42 is 4/3. So inserting it inside our formula, we are going to get this here, and computing this gives us root 5/5. So we are still working. So to get our second H, it's given us I minus 2 W transpose T. So know that transpose. So know that our W transpose is given us this as we have here. We know that. And you see, for the second iteration, W1 and W2 are both 0. So that means anything which contains W1 and W2 will be equal to 0. Since a product of 0 and anything is 0. So that means you have the whole of this giving us 0, the whole of this giving us 0, the whole of this giving us 0, and the whole of this also giving us 0. So that means you're going to be left with something like this. I know that we already have W3, W4, we've computed them. So remember, this is our W3 here, and this is our W4, right? So we have whatever we have here, as I said. So when you find W3 squared, the W3 you computed, when you find the square of it, you get 2/5. When you multiply W3 and W4, you get 2/5. W3, W4, 2/5. And when you find the square of the W4, you're going to get 1/5. So this happens to be your W transpose matrix. But know that our H of 2 is equal to I, which stands for the identity matrix, minus 2 WW transpose. So this is our I minus 2, and this is our WW transpose, right? We just computed that here. Alright, I hope you are following. So after making this computation, you are going to get this H matrix here. Alright, so since you have this H matrix here, that means you are good to go. So to find your second transformation matrix, which happens to be the last, because you are doing just two iterations. So your A of 2 will be equal to H of 2, A of 1, then H of 2. And this is your H of 2. And your A of 1 is what we computed after the first iteration. So let me show you that. So this one, right? So you realize that you multiply H by A by our H again. So we first do this two matrix multiplication, and we end up with this matrix here. And after that, we multiply it by this. So that's what you can see here. And after multiplying these two 4 by 4 matrices too, we get this system here. So this to be our A of 2. So you realize that now we have a tri-diagonal system because we have 0 here, 0 here, and 0 here, 0 here, 0 here, and 0 here. So this happens to be our tri-diagonal matrix that we were finding for. So you could see that with the algorithm for the householder, we've been able to transform or change our symmetric n by n matrix, 4 by 4 matrix into a tri-diagonal matrix. Okay, and as I said, you remember that before we started, we found for the determinant of A from the question, and it was negative 37. So when you find the determinant of this A of 2, which is equal to our tri-diagonal matrix, you're also going to get negative 37. You can try that out. When you find the determinant of this matrix here, you get negative 37. So what this means is that everything that you've done is correct because we have a tri-diagonal system, and the determinant of the tri-diagonal system is equal to our original matrix. So that's how to verify if what you've done is correct or not. So after doing the iterations, if you get something which is not a tri-diagonal matrix, that means you might have made a mistake somewhere and you have to check to rectify that. So thank you very much. Don't forget to like the video and subscribe to our YouTube channel. Bye bye.